All right, we are going to be solving the question above. The question says two rectangular plates, one of steel and the other of brass, each 40 mm wide and 10 mm deep, are placed together to form a beam 40 mm wide and 20 mm deep. Hold on, let's understand that part. All right, the question is telling us that we have two rectangular plates, which one is brass and the other one is steel, and the dimension of the rectangular plate is the wideness is 40 mm and the depth is what, 10 mm, which is same for the two. You can see this is our brass and this is our steel, and the wideness is 40 mm and the depth for the brass here is 10 mm. The depth for the steel is also what, 10 mm. All right, and then when you join them together, when you place them together, you are going to see that the wideness of the rectangular plates will remain the same, which is 40 mm, and of course the depth now, if you sum this 10 mm plus 10 mm, you are going to have 20 mm. I hope you understand that part. So now I said they are placed on two support 1 meter apart. You can see this is two support which is 1 meter apart. All right, the brass plate being at the top of the what, of the steel plate. You can see our brass plate is on the top of the what, of the steel. So now we want to determine the maximum load which can be applied at the center of the beam if the plates are 1, separate and can bend independently, and 2, we are going to consider another case which is firmly secured throughout their length. And then we have the maximum allowable stress in steel to be what, 112.5 Newton per mm squared, and in brass we have it to be what, 75 Newton per what, mm squared. And then we have the modulus of steel and the modulus of brass given to us. So here is all the given data that is given to us. All right, so let's go back to the first case. So we start with case 1, when they are separate and can bend independently. So when you separate these two rectangular plates, when you separate them, it means that each of these plates is going to have its own neutral axis. I hope you understand. Each of them is going to have their own neutral axis. So we are going to assume that their radius of curvature is equal. I hope you still recall radius of curvature from our Flegerer equation. From this equation, if we have stress, we have our stress all over y. This will be equals to what? This will be equals to E all over what? R. And this is our stress. This is the distance from the neutral axis to the topmost part of our beam. This is our modulus of elasticity, and this is our radius of curvature. So if we make our radius of curvature the subject here, the radius of curvature will be equals to what? It's going to be equals to stress all over what? So it's going to be equals to stress all over y multiplied by, sorry. All right, so it's going to be E over y rather. All right, so that is what we are going to have. And you are going to recall from our derivation class, which is part of the introduction to this class, we have derived some formulas. And if you have not watched that, please, I will want you to go over that. So there we said the radius of our steel will be equals to the radius of wood. So now that we are having two rectangular plates, which is brass and steel, so it means that the radius of curvature of the brass must be equals to the radius of curvature of the what? Of the steel. So the radius of curvature of steel, which is this, so that is the stress in steel all over the modulus of elasticity in C multiplied by the distance of the steel, the neutral axis to the topmost part of the steel, which will be equals to the stress in the brass all over the modulus of elasticity in the brass, then YB. All right, so that's it. All right, now, so you are going to take note of something here, that our YS will be equals to our YB. Now let's look at it. The distance from the neutral axis to the topmost part of our base here, if you divide this by 2, you are going to have 5. If you divide this by 2, you are also going to have what? You are going to have 5. So if they are equal, it means that YS will be equals to YB. So it means this will go with this. Then we'll be left with this stress in the steel over stress over the modulus in the steel to be equals to the stress in the brass over the what? The modulus in the brass. All right. So if we can therefore rewrite this as the stress in the steel. The stress in the steel. Okay, let me just rearrange. Let me take this down here. So all over stress in the brass will be equals to, all right, the modulus in the steel all over the modulus in the brass. All right. So I hope we understand this. All right. So now don't forget we already have the value for the modulus in the steel and the modulus in the brass. So if we make our substitution here, we are going to have this. We are going to have this to be equals to 2. This is going to be 2 multiplied by 10 to the power of 5 divided by 8 multiplied by 10 to the power of 4. All right. So that's what we are going to have. So if you divide this by this, what are we going to have? So we are going to have our stress in the steel over the stress in the brass to be equals to 5 minus this, that is 1, 2 here 1, 2 here 4. So 1 divided by 4, that is 0.5. If I multiply that by 5, so I'm going to have this to be 2.5, right? Yeah, 2.5. So, yes, so, yeah, oh yeah, 2.5. So this is going to be 2.5. All right. All right, so we are going to have this to be 2.5. All right, now you are going to take note of something here carefully. All right, now if we assume our maximum allowable stress in the steel to be 112.5. So what will now be the bending stress? What will be the bending stress? So if the allowable stress in the steel is 112.5 Newton per mm squared, that is given to us there here. All right, so let's find what our stress, the stress in the brass is going to be. All right, so the stress in the brass, if you make the stress in the brass the subject here, is going to be the stress in the steel all over 2.5, so which will be equals to 112.5 divided by 2.5. And if you divide this, you are going to have your answer to be 45. So we are going to have this to be 45 Newton per mm squared. All right, so that is what we are going to have. And if you look at this, this is below the liable stress that is given to us here, which is 75. Is that clear? So this is what we are going to use, because if you assume, if we use the stress in the brass to be 75, so if it is 75, it means that the stress in the allowable stress in the steel will be 2.5 multiplied by 75, and 2.5 multiplied by 75, that is going to give us 187.5. Is that clear? And 187.5 will be greater than the what? The allowable stress that is given to us here. Is that clear? So that is why we are not going to be using 75. I hope we understand. All right. All right. So now the next thing we are going to do now is to calculate the moment of resistance of the section, because the question says we should determine the maximum load. Okay, we are going to determine the maximum load which can be applied at the center of the beam, and in the following case. Okay, the first thing we are going to do is to find the moment of resistance of this section. All right, so moment of resistance. All right, so you can say total moment of resistance is going to be equals to the moment of resistance of the steel plus the moment of resistance of what? Of brass. All right, you are going to recall again from our Flegerer equation. We already derived a formula from our what? From our moment of resistance. You know that your moment of resistance is stress multiplied by what? The moment of inertia all over what? All over y, from the formula that says that the moment of resistance is equals to stress multiplied by what? Section modulus. And you know the section modulus there, which is Z, is nothing but what? It's nothing but moment of inertia over what? Over Y. All right. This is what I'm saying. We know that our moment is equals to stress multiplied by Z, right? And this our Z is the same thing as what? I over Y. All right. I hope you understand now. So this is the formula we are going to be using to solve for this too. So let's go for the moment of resistance of the steel now. So the moment of resistance of steel will be equals to the stress in the steel multiplied by the moment of resistance of the steel section all over what? All over Y subscript S. All right, so let's go. Now, the maximum stress of the steel, we've already solved that, which is going to be what? 112.5. So this is going to be 112.5 multiplied by the moment of resistance. All right, the moment of resistance here is going to be the moment of resistance of a what? Of a rectangular section. And what is the formula for the moment of resistance of a rectangular? It is what? BD cubed divided by what? By 12. All right, so now let's go. This is our steel, right? So the base is what? 40, right? And the depth is what? 10. So we are going to have this to be what? BD cubed, that is 40 multiplied by 10 all cubed over what? Over 12. All right, so that is what we are going to have. You can just say all of this over 12. All right, so if you press this directly in your calculator, you are going to have this to be what? 75,000. All right, 75,000. So this is going to be Newton mm. All right, so that's what we are going to have. So now let's go for the moment of resistance of the brass. All right, so this is also going to be the same as this formula that we are using, but it's going to be the stress in the brass multiplied by the moment of resistance of the brass section all over Y subscript B, which is going to be equals to this is going to be 45 multiplied by the moment of resistance is also going to be the moment of inertia rather. The moment of inertia is going to be what? BD cubed divided by what? By 12, which is going to be the same as that of the what? Of the brass, because the base, that is the wideness of our steel, is also 40 and the depth is what? 10. So it's going to be 40 multiplied by 10 cubed divided by what? By 12. All right, so if you do the math, you are going to have nothing but what? I'm going to have 3,000 Newton mm. All right, so that is what you are going to have. All right, so if we proceed, I think it will be better for us to convert this to be in meter. So if we take it to be in meter, we are going to divide this by 1,000. We divide this by 1,000. Oh, sorry, this is 30,000 rather. All right, this is 30,000 Newton mm. All right, so if we take it to be in meter, this is going to be 75. It's going to be 75 Newton meter, and this is going to be 30 Newton meter. All right, so that's what we are going to have. All right, so we can therefore find what the total moment of resistance now, which is going to be 75 plus 30. So this is going to give us what? 105. So it's going to give us 105 Newton meter. All right, so that is what we are going to have. All right, so now you are going to recall from our maximum bending stresses in a beam. I have explained this formula that I want to write now, and I would love if you can go back and check all of these formulas so that you will not just be cramming, because I hate a situation whereby students cram a lot of formulas and you don't even understand what you are cramming. You understand? So that is why Tutor Jerry is here to simplify every concept. Exactly. So what I want to write now is not a rocket science. It's not a magic. It has already been proven by me. I've proved it in our introduction class. So please, I will urge us, if you are just watching our video for the first time, please to go and check all of this stuff out. All right. So if we have a simple supported beam that carries, now if you have a, they said this is what the question is all about, right? Now we want to know the load that will be placed at the center of this beam. Exactly. So if I put a load here, downward load here, I don't know the weight. You understand? That is W there. I don't know W there. So how will I know W? But I know a clue because they already said it's at the center. Exactly. So for a beam that carries for a simple supported beam that carries a load at the center, what is the maximum bending moment? The maximum bending moment is WL divided by what? Divided by 4. All right. So for load, that is, let me just write it for us. For load applied at the center. All right. So the maximum bending moment is equals to WL all over 4. So if we make our L the subject here, L will be equals to 4 multiplied by maximum bending moment divided by, it is the load that we want to calculate, right? So we are going to make W the subject, not L. We already know the length, which is 1 meter. So divided by L. So now this will be 4 multiplied by, so the maximum bending moment now is going to be the moment of the section now. The moment, that is the moment of resistance here. Exactly. So it's going to be 105 divided by 1. All right. So now if you press that in your calculator now, what will be our W? Our W will be equals to what? It's going to be equals to 420. So it's going to be 420 Newton. All right. So this is the solution for case 1. So we are going to consider case 2. We're going to clean the other side of the board. All right. We are going to consider the second case, which says that firmly secured throughout their length. Please listen and understand what they are trying to say there now. All right. So if they are firmly secured throughout their length, it means that this rectangular plate, when they combine them together, they form a single unit, which means that they are going to have the same neutral axis. Is that clear? So now we are going to need now to convert this composite section now into an equivalent brass section. All right, so that all the entire section will not be different. That is, the plate will not be different. Is that clear? All right, so we just have brass throughout. Is that clear? So how do we do that? How do we convert this composite section into a brass and into an equivalent brass section? We are going to do that if we know what our modular ratio is. What is our modular ratio? Our modular ratio is that is the modulus of the steel divided by the modulus of the brass, which is nothing but what? 2.5. When we divide this the other time, it's giving us 2.5. So we are going to be multiplying the wideness of the steel by modular by 2.5. Exactly. By the time we multiply that, we are going to convert this the steel part into a what? Into a brass section. We are going to convert this composite section into a what? An equivalent brass section. So we just need to multiply this by this 40 by what? By 2.5. And if we do that, we are going to have 100 mm. So it means if we are going to draw the diagram now, it means the wideness of this steel section now is going to be bigger. It's going to be 100, while this brass will just be on top. I hope you understand. So I'm going to draw the diagram for us to understand the clear picture. All right, so here is the diagram for the equivalent brass section as explained. All right, so we are going to be calculating y bar. And what is y bar? Y bar is the distance between the center of gravity of the equivalent brass section and the bottom face of the section. All right, and what is the formula for y bar? You are going to recall that our y bar is what? A1 y1 plus a2 y2 all over what? All over a1 plus a2. All right, so this will be equals to, so let's divide this section into two. Let's say this is 1 and this is 2. All right, so our a1 is the area of the first section, which is a rectangular section. And what is the area of a rectangle? It is what? Length times what? Breadth. So this is going to be 10 multiplied by 100, which is what is going to give us what? 1000. All right, so that is our area. And y1 multiplied by y1. What is y1? Y1 is the distance from the bottom surface to the neutral axis. If I draw the neutral axis of this rectangular section, from the neutral axis to the bottom is going to be 10 divided by 2, which is what? 5. So plus a2, the area of the second rectangular section is going to be 40 multiplied by 10, which is what? Which is going to give us 400. Then multiply by the neutral axis here. The neutral axis is going to be at the top here, and we are moving from the bottom, right? So from this point to this point is 10. 10 plus, and then if we divide this by 2, we are going to have 5. So our y2 here is going to be 10 plus 5, which is 15. So we are going to have 15 here, then divided by, so it's going to be a1 plus a2. That is, our a1 is 1000 plus what? Plus 400. All right, so that's what we have. So if you press that in your calculator, you are going to have the value to be 7.86. So we are going to have this to be 7.86 mm. All right, so that is what we are going to have. So the next thing we are going to do is to find the moment of inertia of the equivalent brass section. And then we know that our moment of inertia is going to be equals to the moment of inertia of the first section plus the moment of inertia of the second section, right? All right, so and we are going to apply the formula for the moment of inertia here. So this will be equals to, so I will be equals to, now for the first section we are going to have, because we know that the individual rectangle section is having its own neutral axis, right? So it is not the section is not at the center, or it's not at the center. Do you understand? So it means that we are going to apply the moment of inertia, the formula for the moment of inertia of a rectangle, that we involve y bar minus y1 all square and so on. All right, so let me write the formula for a1. We are going to have this to be bd cubed over 12. So you can just put 1 here plus what? Plus a1 into, now if you check our y bar, is y bar greater than y1? Our y bar is 7.86. Our y1 here is what? 5. So this is going to be y bar minus y1 all squared plus, we are going to apply similar formula for the second section too. So this is going to be b2 d2 all cubed over 12 plus a2, then you are going to observe that our y2 is greater than our y bar. So we are going to have y2 minus y bar, so all squared. All right, so that's what we are going to have. So if we substitute, we are going to have the moment of inertia of the section to be b1 is the base of the first rectangle section, which is 100. So we are going to have 100 here multiplied by D1, which is 10 cubed divided by 12 plus A1. Our A1 is 1000. We are going to have 1000 into our Y bar here. What is Y bar? Y bar is 7.8. So we are going to have 7.86 minus Y1. What is Y1? Y1 is 5 all squared plus B2. That is the base of the second rectangle section is 40. So we are going to have 40. Then the depth is 10 cubed over 12 plus A2. What is A2? A2 is 400. So 400 into, this is supposed to be in bracket. So into Y2. Y2 is 15. So this is 15 minus 7.86 all squared. Alright, so that's what we are going to have. So our moment of inertia now will be equals to, so if we press all of this stuff directly in our calculator, we are going to have a moment of inertia to be 40,238.1. So what will be the unit? The unit is going to be mm to the power of 4. All right. So that is our moment of inertia. All right. And again, before we proceed, this Y bar is 7.86. So this 7.86, we can also say it is the distance of the lower extreme fiber. That is the distance of the lower extreme fiber. That is from the bottom part. So we can say, and if we please let me retake this again. I said this our Y bar is the distance between the center of gravity, right, of the equivalence brass section and the what? And the bottom surface. So 7.8. So since the total distance that we have here is 20, and then we are saying from the bottom surface is 7.8. So 7.8 will be definitely around somewhere here. It's not even up to 10. We need to be around somewhere here. So for us to get the distance now, for us to get the distance of the upper extreme fiber is going to be 20 minus what? Minus 10. All right. So let me write the distance. That is the distance of the upper extreme fiber. All right. So is equals to 20 minus 7.86. So if you subtract 7.86 from 20, you are going to have 12.14. So this is going to be 12.14 mm. All right. So the distance of the lower extreme fiber is 7.86. Distance of lower fiber is equals to 7.86 mm. All right. So maybe I'm going to be cleaning this side for us to proceed. All right. So you are going to take note of something here. We know that the allowable stress in the brass is given to us as 75 Newton per mm square. And if you look at this brass in equivalence section, the top part here is of brass. So which means that the stress at the top fiber there will be what? 75 Newton per mm square, right? So which means that our stress there is going to be what? 75 Newton per mm square. All right. So, and then we know that it is of brass, right? So now what will now be the stress at the lower fiber? All right. So the stress at the lower fiber now, the stress at the lower fiber, let's say this is our lower fiber, is going to be is going to be, that is 75, that is the stress in the brass, which is 75 multiplied by the distance there of the lower fiber, that is the distance of the lower fiber there is what, 7.86 divided by the distance of the upper extreme fiber, which is 12.14. So if you press this in your calculator, what are you going to get? You are going to have 48.56 48.56 Newton per what? Per mm square. All right. So this is the stress in the lower most fiber in the section, right? All right. So, and you are going to recall that this section too is also of what? Of brass. Is that clear? So if that part is of brass now, so how do we convert this stress now that we have to what? To be of steel. Is that clear? All right. So for us to convert it to be of steel, don't forget, by the time we multiply it by the other time by what? Modular ratio. So we are going to need to multiply this by modular ratio so that we are going to know the stress in the steel section, because it is actually steel. Do you understand? That was converted. All right. So if we multiply this by 2.5 now, 2.5 multiplied by 48.56 is going to give us 100 and so it shows that the stress in the steel section there is going to be 48.56 multiplied by 2.5. So this is going to give us 121 point is it 0.5? 0.4 rather, Newton per mm square. All right. So if we therefore compare this with the value that is given to us here, you are going to see that it is above that value there. So it means that the stress in this section will not be fully stressed. Is that clear? So what we are going to do is, if we take the maximum stress in the steel at the bottom to be 112.5, we take it to be 112.5. So what will now be the equivalence what will be the equivalent stress in brass? So that's what we are going to do now. So if we take our stress to be 112.5 at the bottom, so what will now be the equivalent stress in brass to this? So that's what we are going to do. So there, our equivalent stress of the brass will be equals to, is going to be equals to, if we take it to be 112.5. So we are just going to divide this by 2.5. So if we divide this by 2.5, we are going to have what? 45. So that is going to be 45 Newton per what? Per mm squared. All right. I hope we understand all of this analysis. So now what we are doing is that we are taking the stress at the bottom of this section now to be 112.5. So which is still here, right? So if it is still here, how do we now get the corresponding brass stress? So we are just going to divide that by 2.5. So, and if we divide by 2.5, we have 45 Newton per watt per mm square. So this is the stress that we are going to be using to solve this question. All right. So we are now going to be using our flexural equation now. Then we solve for the maximum, the moment of resistance there. So I'll need to clear that. So you are going to recall that our moment of resistance or maximum bending moment is equals to what? Is equals to stress multiplied by moment of inertia divided by y. So this will be equals to the stress we are using now for the stress. The stress we are using now is the brass stress. So which is 45. So it's going to be 45 multiplied by the moment of inertia is 40238.1 divided by our y. So what will be our y? Our y is going to be 786. Sorry, 7.86 rather. 7.86. That is our y mass. Sorry. This is the distance of the lower fiber. I've already explained that to us. It is 7.86. Alright, so if we do this, we are going to have our m to be equals to what? So 45 multiplied by 40,238.1 divided by 7.86 is going to be what? It's going to be 230,370.8. So the unit here is going to be what? In Newton mm. So you can actually take it to be in Newton meter by, if you take this point, if you divide by 1,001, 2, 3. So it's going to be 230. This is going to be 230.3708 Newton meter. All right. So again, we are now going to apply the formula that we apply for when a simple supported beam carries a that carries a point load at the center. So M there will be given that WL divided by what? By 4. So if you make our W the subject there, W will be equals to 4M divided by what? 4M divided by L. So if you substitute now, we're going to have 4 multiplied by 230 point what? 0.3708. Our L is 1, right? 1 meter, 1. So if you do this, you are going to have your answer to be, so it's going to be 921.48. So it means that our W will be 941.48. So this is going to be in Newton. So here is the solution to the above question. So I believe you understand this clearly. And if today is your first time of coming across our content, please don't forget to give this video a thumbs up. And if you have any question on this part, maybe that is still giving you any confusion, you can comment that in the comment section. And if you truly understand this, let us also know in the comment section. And please don't forget to share this content with your friends who might be in need of it. Thanks. Stay tuned for more.